minus L, which is 6, is less than epsilon. So that part is okay, right? I didn't write it all out. For every epsilon greater than 0, there exists a delta greater than 0 such that if this, then that. So this, and this is not going to be on today's quiz. We're going to have a review day before that. So for I should probably write this out. Every epsilon greater than 0, there exists a delta greater than 0 such that then it's the line above. If this, then if this, then this follows. So you start off with this, the second part. Well, let's see, we can factor the top. X minus 4's cancel out. Two minus 6 is negative 4, so you get x minus 4 less than epsilon. So it looks like we got the left side to look exactly like what we have up here. So to start the proof, we're going to say delta should equal exactly epsilon. Then in that case, if absolute value of x minus 4 is less than delta, then absolute value of x minus 4 will be less than epsilon. Now, from this point forward, what you do it over here is you just work your way back up. You have it over here, then you're going to write this line, then you're going to write this line, then you're going to write that line, and then you'll be done. Did the fraction throw you off right here up here?
Yes.
No, I see now. I understand. I got it. Thank you.
Well, I'm almost done. So then you would just write, x plus 2 minus 6 is less than epsilon. And then you keep going, and then eventually, x squared minus 2x minus 8 over x minus 4 minus 6 is less than epsilon, and then therefore you prove it. All right, any questions on 2-3?
Yeah, number 27.
And don't worry, the delta epsilon, we'll do another one the review day. Number 27. All right, we'll do 27 and we want to move on because I don't want to
really fast, Professor, before you move on, is this where you're supposed to write the LIM x equals 4 or goes to 4, like before everything?
Yeah, right here.
Okay.
Yeah. Therefore, L limit as x approaches 4 and whatever all of this right here.
Okay, thank you.
Uh-huh. You said 27, right? On section 2-3?
Yes.
Limit as x approaches 16 of 4 minus square root of x over 16x minus x squared. So if you remember, I said when you got, well, so the bottom you can factor out an x, but that doesn't really help much initially. So remember I told you when you can't factor it and you see a radical term, so in this case, the top has a radical, we'll multiply top and bottom by the conjugate of the numerator, because that's the side that has the radical. So 4 plus square root of x over 4 plus square root of x. So then what we'll do is the bottom, you just leave it in factored form. And the top, well, that's just, they're conjugates of each other. So it's just going to be first term squared minus last term squared. Square root of x squared is x. So then the 16 minus x's cancel out. So you got limit as x approaches 16 of 1 over x times 4 plus square root of x. So then from here, just plug in 16.
Okay, so whenever we cancel out the top completely, it just equals to 1 then?
Yeah, there's always a 1 left. Yeah, because if you put
Okay.
0, then the whole thing goes to 0.
All right, that's where I was confused. I kept putting 0 and then, yeah, okay.
Yeah.
I got it. Thank you so much.
Well, I'm almost done. So 4 plus 4 is 8. So you got 16 times 8. So you get 128. So 1 over 128.
Thanks.
So yeah, so let me explain to you why. I mean, so if you have like, let's say a fraction of like 2 over 10, right? You agree that that reduces to 1/5, right?
Yes.
Okay. But if I were to use your logic and go cancel this, I can't say it's 0 over 5, right?
Yeah, that's right.
Okay. So what's happening is you're removing a factor of 1. So this 2 is really 2 times 1. So the 2's cancel out, but you have a 1/5 left.
Got it. Thank you
All
so
right.
much.
Let's go ahead and continue on with the rest of section 2.4 or 2.3, I should say. Sometimes some days I can answer more questions, but today I noticed I was going to run out of time. But you know, you have SI and you have the math lab as well, and we'll have a review day before the exam. So 2.3 continue. If I ask you what's the absolute value of 4, the answer is 4, right? Whereas if I were to ask you that what's the absolute value of -4, the answer is still 4. Because when you take the absolute value of a number, I'm asking you how far is that number away from 0. So 4 is exactly 4 units away from 0. -4 is also exactly 4 units away from 0. So since the absolute value of something represents a distance, it's got to be positive, or at least 0. Now, so the definition of absolute value is absolute value of x. You know, sometimes it's in a straight line. I don't know how that does that. You know how I just made a straight line like that? I don't know.
If you hold it down when you're drawing, it'll make into a straight line.
Oh, okay, press it. So it's oh wow, okay. So the same thing with a circle probably, huh?
Yeah, so if you make any shapes and hold it down, it'll make it perfect for you.
But it didn't do it this time.
You have to hold it down after.
Okay, good enough. I'll play around with this later. So absolute value of x is equal to, oh, you have to hold it down after or before?
After.
Oh, okay. Well, let me try this again. Nope.
I think your iPad's broken.
All right, absolute, I probably did not do it right. Absolute value of x is equal to x if x is greater than or equal to 0, or it's equal to negative x if x is less than 0. So basically, it's the same thing that I just said here. When I took the absolute value of 4, it was exactly 4 because 4 is a positive number. So absolute value of x here is exactly itself when x is greater than or equal to 0. But it's equal to its opposite if x is less than 0. So in this case, since negative 4 is less than 0, it's equal to its opposite when you take the absolute value. So this is the definition of absolute value right here. So now we're going to move on and do a problem. So the question that I'm going to do now is, this is number 42 from the book. So when you do number 41 and 43 for homework, you can kind of use this as a guide. Limit as x approaches negative 6 of 2x plus 12 over the absolute value of x plus 6. We want to know what is that equal to. Hey June, what happened? Do you have a weak internet connection? That's why no video? Seems to be the theme.
Oh, sorry, I forgot to turn it on.
And I'm sorry, I forgot to give you full credit on the quiz. I'm just joking. We want. I want. See the thing is, Hey June, you sound like a good student, whereas with the people here, H, Ram, Bryant, Elizabeth, Daniel, I don't even bother them. They're just here as a
Facts.
warm up. As what?
Those are facts. I'm just kidding.
Yeah, they're the riffraff. They're just here to warm up when they really take calculus seriously the next semester.
Exactly.
All right. Oh yeah, so here's the problem with this problem, number 42. You see how there's an absolute value of x plus 6 on the denominator? Well, limit as x approaches negative 6. Well, that absolute value is bothering us, right? That's what makes this problem a little bit more difficult. So what we got to do is split this up into two problems. We're going to take the limit as x approaches from the right side and the left side. But before I do that, let me explain. Let's deal with this absolute value. What's the absolute value of x plus 6 equal to? Well, it depends. It's equal to exactly x plus 6 if x plus 6 is greater than or equal to 0. If then from there we can conclude x has to be greater than or equal to negative 6. As I move the 6 over. But also absolute value of x plus 6 is the opposite of x plus 6 if x plus 6 is less than 0. And from there we can conclude, or that implies x is less than negative 6. So now let's go to the problem here. We're going to split it up into two problems. Limit as x approaches negative 6 from the right side of 2x plus 12 divided by absolute value of x plus 6. So I'm going to figure out what the limit is from the right side, and then I'm going to figure out what the limit is from the left side afterwards. And if they're approaching the same number, then that would be my answer. If they're approaching different numbers, then I would say does not exist. So in this case, from the right side, what is this equal to? Well, let's take a look. From the right side of -6, we're talking about numbers like -5, -4, numbers that are larger than -6. So that would be this guy right here. So that would mean absolute value of x plus 6 will be equal to x plus 6 right here. So this is equal to the limit as x approaches -6, that's a negative sign here, from the right side of 2x plus 12 over x plus 6. So once again, so this absolute value of x plus 6 is just x plus 6 because we're going from the right side. And from the right side, we're talking about values that are larger than -6. So this is what applies. All right, now, continuing on further, limit as x approaches -6 from the right side. Let's factor out a 2 up top. X plus 6's cancel out. So we're left with limit. Well, I mean, the answer is just 2, right? Limit as x approaches -6 on the right side of 2 is just 2.
Professor, I was wondering, can you walk through this problem one more time? Just like talk
Yeah.
it out. So I'm still really confused.
So starting from here. Okay, so we're going to go limit as x approaches -6 from the right side. When we're going, visualize where -6 is on the x-axis. It's to the, what's the right of it? -5, -4, those numbers are to the right of -6. Well, what do numbers like -5 and -4, they're greater than -6. So this is what absolute value of x plus 6 is going to equal when we're to the right of -6. So that's why I went ahead and replaced the absolute value of x plus 6 with x plus 6. And from here, you just factor the 2 up top, x plus 6's cancel out, and we're left with 2.
Thank you.
Now, in the scenario where you got limit as x approaches -6 from the left side now of 2x plus 12 over the absolute value of x plus 6, well, in this case, we're talking about values to the left of -6, numbers like -7, -8. Numbers like -7 and -8 are less than -6. So in that case, absolute value of x plus 6 is going to be equal to the opposite of x plus 6. So we got that's equal to limit as x approaches -6 from the left side of 2x plus 12 over the opposite of x plus 6. And then you just go ahead and simplify this as well. So you got limit as x approaches -6 from the left side, factor out a 2. So now the x plus 6's cancel out, and we're left with, well, 2 divided by -1, which is -2. So notice from the right side, we want to 2. From the left side, we want to -2. So therefore, going back to the main question up here, the answer is going to be does not exist. Because from the right side and the left side, they're not hitting the same number. I know it's kind of not motivating when you do all this work and you get does not exist. Like you want to show a number for it. Oh, I haven't done this for this class yet, but Daniel, know this, the official drink of all my math classes are Coke Zero. The best soda ever created?
Pepsi, wild cherry, diet.
Nice plug there. Nice plug.
It tastes better than Diet Coke, and it doesn't have the sugar of regular Coke.
It's been a while since you've done that, actually.
Wait, you didn't have me last semester.
Yeah, but I had you for like 2 semesters ago. And even in the college algebra, you did the same thing. You would like advertise the drinks that students
Yeah,
would.
well, that's why you haven't seen me in a while. You weren't in my class last semester.
I know.
All right. Madison, I'm sure you've heard stories.
Yes, I have.
But what are you majoring in, by the way?
Me, I'm majoring in political science and German. So not math,
Political science.
unfortunately.
Do you want to be into international politics with Germany?
I mean, that would definitely be cool. I think that would definitely make me use my German practically. So hopefully some interaction with Germany in politics would be nice. Yes.
Oh, okay. Or do you want to just, after you graduate, go to Oktoberfest in Munich?
Yes, I'll just drink beer. That will be my only commitment to the German classes I took.
Kirkland water is dank. Is dank a German word? No, danke means thank you. I don't know what dank means. All right.
So for this problem, are you just doing both?
Yeah, so for the absolute value problems, like number 41 and 43, you have to like split it up and do from the right side and left side separately, because the absolute value, it depends. If you're coming from the right side, this part right here is going to be equal to that. But if you're coming from the left side, this is going to equal that. So that's why you have to split it up into 2 cases.
Oh, I see. This is just another way to find that point if they meet or not without a graph, I guess, right? What were we doing before?
Yeah, I mean, if you knew how to, well, even if you were graphing it, you'd have to split it up so you can see how the graph looks like to the right and left.
Oh,
I mean,
okay.
Unless you have a graphing calculator, but you normally would say in the old days, if you didn't have a graphing calculator, you'd have to split it up into 2 cases and then graph it like a piecewise function.
Okay, that makes sense. Okay.
All right, moving on. So one other thing that I want to make sure you guys cover is, by the way, I want to make a quick change to the homework assignment for section 2.3. So on 2.3, on the homework sheet, I said do 1, 11 through 27, 37, 39, 41, 43. So you can cross out number 39, but add 53A. All right, so here's what I want to talk about this next, same section still. There's this is called, it's this like fancy looking bracket. It looks like you have double vision. It's called the greatest integer function. The nickname for it is the step function. And it comes up periodically throughout your math classes. We're trying to see how come it's not a straight line. Okay. Right. So this is how it looks like. I'll explain to you what this means. Greatest integer function is what's the greatest integer that's less than or equal to the number that we're talking about. So for example, let's say we're up here at number at 1.5. What's the greatest integer? Integer, think whole number, but it could be negative as well. What's the greatest integer that's less than or equal to 1.5? Well, let me wait a second until you guys draw the graph. Sorry. Hold on. Are these notes or is it a specific problem? Well, 53A is a specific problem that you got to do for homework. Now this is notes, which will help you for number 53A. Rainwater is the best. Thank you, Miguel, for your input. Rainwater. I meant Miguel Cerritos with the rainwater is the best, but Miguel Lopez with a legitimate question. All right. So, for example, if I asked you what's the greatest integer function when you apply 1.5, it would be 1, because the largest integer that's less than or equal to 1.5 is 1. What is the largest integer that's less than or equal to 1.9? It would still be 1. But once you hit 2, the greatest integer that's less than or equal to 2 would be 2. So that's why it jumps. So all the way here from 1 all the way to 1.9, 1.99, it's 1. But once you get at x equals 2, it jumps to 2 because now the greatest integer that's less than or equal to 2 would be 2. All the way to 2.1, 2.2, 2.5, 2.8, 2.9, the greatest integer that's less than or equal to any of those numbers is 2. But once you hit 3, the greatest integer that's less than or equal to 3, once you hit 3, it will be 3. Does that make sense? So you can see the nickname is a step function because it looks like steps. Anyway, so this is like this is universal, meaning like it comes up through different math classes. You just know that notation means the greatest integer function. So on question 53A, you'll have a greatest integer function. You'll be asked a series of limit questions. So you kind of have to visualize how the graph looks like. So now you know how the graph looks like. Let's move along to now the squeeze theorem. Same section still. If f of x is less than or equal to g of x, which is less than or equal to h of x, and limit as x approaches a of f of x equals the limit as x approaches a of h of x, which equals L, then we can conclude limit as x approaches a of g of x also equals L. And I'll draw a picture to show you. All right, so here's the explanation. So notice if I'm given that f of x so if I'm given f of x is always less than or equal to g of x here, and it's always equal to less than or equal to h of x. So then what happens is here you got f of x, and you got h of x. I don't know if that helps. And then g of x is always trapped in between the two. I like the other one. Okay. So then so notice g of x is always sandwiched between f of x and h of x. So if I can conclude that if I'm given that limit as x approaches a of f of x right here is equal to L, and limit as x approaches a of h of x is equal to L. So basically, if the top graph is merging to a certain number, and same with the bottom graph, the squeeze theorem says, hey, this graph that's sandwiched between the two has to be going towards the same number, right? If I have a graph that's really high and another graph that's really low, they're going towards the same number. Well, the one that's always trapped between the two has to be going towards that number by the squeeze term. Does that make sense? Okay,
Yeah.
so that's the squeeze term. Now, when you would apply this is this. Sometimes you know the limit of some two other functions, and you don't have a mathematical way to prove that the limit of some function that's in between them. So by the squeeze theorem, you can say, hey, because this is always in between these two functions, and I know these two functions are going to 0, so therefore this has to be going to 0. So, for example, like let's say you have some graph that looks like this, like that's your f of x. And let's say you have another graph that looks like that, that's your h of x. And then you have another graph, let's call it g of x, that's going like this. And it's always trapped between the two. Well, then you know that it's going wherever these two are going because it's crunched between them. That's basically what a squeeze theorem says. All right, now let's go over a few things here. A few things you want to make sure you know when you're doing limit problems. Limit as x approaches 0 of sine of x over x equals 1. Now I couldn't find the homework question which you apply this to. In the other book that I teach calculus class in the morning, they have more problems, but let me explain to you just for your own knowledge where this would be used. So you can just always be familiar with that. You don't need to prove it. But for example, if you were asked the question, limit as x approaches 0 of, that's supposed to be 5, I messed that up. If I were to give you 5 sine of x over x, this is an easy one, you would just say, all right, well, I know what sine of x over x is, so I'll just factor the 5 out and say limit as x goes to 0 of sine of x over x which so then I know this gives me 1, so it'll be 5 times 1, and so the answer is 5. By the way, Aaliyah, if you see questions like that, like in another book that I use in the morning, there's like problems like this. Limit as x approaches 0 of like, let's say 7 sine x over 5x, and we have to try to figure out how to do it. Or like 7x in here or something. But I couldn't find them in this book. In one of these sections, there should be something like that. Anyway, maybe I just looked really quickly. Anyway, so the other property that I want you, the other note that I want you to be aware of is limit as x approaches 0 of sine of 1 over x, like that. that does not exist. Now, you don't have to prove it. I'm just going to show you why it does not exist. Because as x gets closer and closer to 0, what happens to sine of 1 over x is just starts going up and down really fast. So it doesn't like merge to 0. It keeps going back and forth from between -1 and 1 really fast. So it's not merging to a number. So that's why the answer is does not exist. So the only reason I'm mentioning that is because you need to know it for this next question that I'm about to do. Because I want to give you an example where the squeeze theorem is applied. A lot of times students ask, hey, can you give us an example with the squeeze theorem? I'm like, I can't think of something off the top of my head. So I have one ready for you to do so you can see where the squeeze theorem is applied. Now, this is not going to be on a quiz or even probably a test, but in case you're a math major, you want to see this, you can. By the way, with German and political science, why are you taking Math 158? Because you just love calculus and math?
It seemed fun. I like doing math. It's entertaining. I don't know.
Oh, trust me, only my class.
Okay, I will believe you on that.
Well, some of the other math professors, trust me, you don't want to be listening to them for 2 hours straight. Well, you know, nobody's recording this, are you? Okay, thank you. Oh, Leah, you didn't hear anything, right? Okay, good.
Nothing at all.
President Greg Schultz, did you hear that?
What year, what semester are you in German?
I actually finished all of the German classes last semester.
Oh, wow.
Yeah.
So my brother took German in high school, and he told me, this is interesting, a lot of people like randomly don't know this, that the English language is derived from German. So it's a Germanic language. It's basically their sister languages, even though they don't sound anything alike. Kind of like Italian, French, and Spanish are sister languages.
Yeah, it's actually really nice when you're learning German because a lot of the sounds are relatively similar and then there's some carryover with words and stuff. So that makes it easier, I think, to pick up the language.
All right. So let's say we want to do this problem right here. Now, I noticed that limit as x approaches 0 of x squared, that's just 0. But sine of 1 over x, so like, here's the thing. You could say, hey, isn't that just limit as x approaches 0 of x squared times the limit as x approaches 0 of sine of 1 over x? Yes, but the problem is, yes, I know this is 0, but this does not exist. And 0 times does not exist is not 0. I mean, I feel like it's 0, but we don't go by what we feel. This is like in math class, you can't do that. You do that in your liberal arts classes. Sorry, Madison. So 0 times any other number is 0. 0 times 1 million, that's 0. 0 times 0 is 0. But 0 times does not exist. You can't say it's 0 with definite certainty. So we have to have another way to do this. So this is where the squeeze theorem comes in play. I'm going to show you. And how do I know to do this? Because, well, someone showed me to do this a long time ago. Now I'm showing you. I mean, and now the first person to come up with it, they're the genius. -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. So sine of something is always between -1 and 1, right? So sine of whatever that is always between -1 and 1. Now what I'm going to do is multiply all three sides of this inequality by x squared. So I get negative x squared, which is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. Now the key is when you're multiplying both sides or all three sides of an inequality, you want to make sure you're not multiplying by a negative, because when you multiply by a negative, you got to flip the symbol. The worst is if you multiply by x, because you don't know if it's negative or not. So then you flip it or you don't flip it. You can't really go that route. In this case, it's x squared. So I know x squared is positive, or at least 0. So I don't have to flip the symbol. Now, I'm going back to the main problem right here. I know limit as x approaches 0 of negative x squared. Well, you just plug in 0, you get 0. Limit as x approaches 0 of x squared, that's also 0. And since negative x squared is always less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared, and that's what I did up here, then by the squeeze theorem, we can conclude that the limit as x approaches 0 of 1 over x of x squared times the sine of 1 over x, that has to equal 0. And that is the squeeze theorem.
So you're saying this limit x squared times sin is the line in between those two?
Yeah, so I'll show you graphically how it looks like, but I gotta scroll down. So let me wait until you copy this out and I'll show you a picture.
Okay.
All right. So here's what happens. Ooh, very nice. I think I learned it. Oh, I thought I had it. Let me try one more time. Yes. I'm not going to even try to do a parabola now. So x squared looks like that. Negative x squared looks like that. So the graph of, I'm just going to show you how x squared times sine of 1 over x is going to look like this. So x squared times the sine of 1 over x is the red graph that's always sandwiched between the two parabolas. So therefore, limit as x approaches 0 of the two black graphs, they're going to go to 0. So therefore, the red graph is going to go to 0, and we showed you right here by the squeeze theorem. All right, so that's finishing up 2.3, and we already did 2.4. So we're going to take a quick break. Then after the break, we're going to do 2.5, and then yeah. So let's take 10 minutes. We'll start back up at 4:16.